Hello again there, chemistry. We've been talking here in chapter 14 about acids and bases, but we really haven't hit very hard just what is an acid or what is a base. And so here on page 455, we start to get into some of the nitty-gritty. And the first thing is the name, Arrhenius. I don't care very much about the name of it because we're going to learn that there are 3 different acids and that there are 3 different types of bases. And we care more about how they become acids or bases than the actual name of that. But this is the most common name or type, and what it is it increases the concentration of the hydrogen ions, or H+, in what? In water, in aqueous solution. So let's take a look at that. So we're going to look at the most famous example, and that is if we have some hydrogen chloride gas and we mix it together with some water, what are we going to get? Well, the water is actually quite attracted to the hydrogen part of this molecule, and it wants to take that hydrogen, and when it does, it becomes H3O. And it leaves chlorine behind, but chlorine keeps the electron, and so hydrogen comes only with the proton, and it forms H3O, or hydronium ion. And it's still dissolved in water. You can see this example right here in your book. Now, our definition said it made hydrogen ions. Well, hydrogen ions don't actually really exist in solution because the hydrogen ion gets stolen right to the water and it forms a new ion, hydronium. Hydronium is a vocabulary word really that we've learned from the last chapter that you should keep on knowing. It was also on page R78 as ions that you should know. The unique thing about this ion is it does not form any compounds. It's not part of any compound. It's created through this process, and so it's unique in that way. Once again, hydrogen shows its uniqueness. So let's take a little closer look here, drawing Lewis dot structures here for hydrogen chloride. Chlorine has 7 electrons and hydrogen has 1. Here again, hydrogen has 1 and 1, and the oxygen has 6. When the reaction takes place, the hydrogen from the hydrogen chloride wants to leave and is attracted to the water molecule. And so what happens is this hydrogen leaves and comes over to here. But oxygen already has all the electrons it wants to have. It's satisfying the octet rule. Chlorine really wants to keep its octet in order, so what happens is this electron stays here, stays right there. So the chlorine winds up with a -1 charge, and the water, which gained only the proton and no electron, winds up with a plus charge. So you have the hydronium plus the chloride ion, and it's because the proton, this increasing of the hydrogen ion in aqueous solution, makes this an acid by definition. And so there's many other things that will do this. Here's nitric acid, and it joins with the water, and the hydrogen goes here, and it loses it. Again, definition of an acid because it loses the hydrogen ion. Now, just because something has hydrogen on it does not necessarily make it an acid. For example, methane has 4 hydrogens that it could lose, and it does not react with water because it keeps all of its hydrogen atoms. It doesn't lose them, so it is not an acid even though it has a hydrogen on it. So just because it has hydrogen doesn't make it an acid. It has to be willing to lose it when it gets into water. How do you know? By experiment and learning. Bases, it says that they increase the concentration of hydroxide ions. Well, here we have bases, the most famous of which is sodium hydroxide. And the sodium and the hydroxide are bonded together in that the sodium is wanting to lose its electron, and the hydroxide wanting to bond to it. And so you mix that into the water, and you get the ion of sodium and the polyatomic ion of hydroxide. The oxygen, just like up here, and the chlorine wants to keep that electron, and so it keeps sodium's electron, and sodium is short one, and that's why it's a positive charge. But increasing this guy makes him a base. Up here we have this is a acid. Now, there's a very unique one right here in your book, and that is NH3, which just because it has a bunch of H's makes you want to think, oh, that might be an acid. But no, what's really funny is that when it bonds together with water, it wants to take a hydrogen from the water. And so you get NH4 with a plus on it, plus hydroxide ion. So you get the nitrogen with the, see, it was NH3, and it has an octet of electrons. It was balanced, and then it took a hydrogen, and that hydrogen didn't bring any electrons with it, so it left it behind with the water. And the water lost its hydrogen that was here. It's gone, but it kept all of its electrons. So this becomes a minus charge, and this becomes a plus charge. So it is the unique one in that it is a base because it does what? It increases its hydroxide ion concentration, just like this guy does. That's what makes it a base. And so you can see easily why all these guys make easy bases, because they're all giving up hydroxide ion making bases, whereas this guy is doing it by taking a hydrogen away from water. Another aspect your book covers here is something called organic acids, and they have a carboxyl group. So another topic touched on in this section is organic acids. Organic acids are acids that contain a carboxyl group. Well, what's a carboxyl group? Well, organic acids contain a carboxyl group. A carboxyl group, you've actually seen this before. Your book talks about here CH3COOH, which I call the Hatchu ion. And there's actually a drawing of the structural formula right up here. I'm going to draw it here. So you remember we talked about that methane does not form an acid because it does not lose any of its hydrogens. Well, we're going to draw something kind of similar. So here's our typical start of a methane atom, and we would normally put another hydrogen right here. But we don't. We actually have another carbon right here. And this is part of the CH3. See, there's the CH3, and then there's the C, double bond O, another O, and an H. So this is the organic part, and this is what we call the carboxyl group. So we could attach this to many carbons. It doesn't have to be just one. This is the most famous, partly because you know it already, as acetic acid. If we take the H off, you know it as the acetate ion. The acetate ion could be bonded to any number of things. It could be sodium acetate, which is what we use to make that hand warming material that crystallized at a low temperature. Well, this is carboxylic acid can lose this hydrogen, and this hydrogen can go away. And when it does, we get the CH3COO, and that's a minus because the hydrogen left and that hydrogen joined the water and formed the hydronium ion. Now this is a weak acid, so we often draw it with an arrow going this way and an arrow going this way, saying it's reversible. In fact, it would rather be this form than this form. This is why we don't mind eating it too bad, because it's not that strong of an acid. It also means if it's a weak a weak acid, it is a weak electrolyte. And this is part of what your book talks about up here is that we've got some very strong acids listed here. Hydrochloric acid, sulfuric acid, which we've talked about, hydrobromic acid. But notice that when some of them, like here is the acetic acid, notice the arrows are going both ways. When the arrow is going only one way, we know that they're trying to say that it is a strong acid. When it's going both ways, we're trying to say that it's a weak acid. Now we'll talk about this more in the next section, but here you see sulfuric acid loses a hydrogen and then it becomes HSO4, which could be that it loses another hydrogen. And so you can come up here and you can see that HSO4 plus water can yield yet another hydronium ion and leave the sulfate ion. But it doesn't want to lose a second hydrogen very willingly, so we call that a weak acid, whereas the first step is a strong acid. All right, that concludes our section on acids and bases and what they are. And we'll see you on the next section.